Now know how to calculate pH for strong acids or strong bases. So today we're going to talk about how we can do that with weak acids or weak bases. And just as with strong, a weak acid is going to cause the pH to lower, just like you would think. And a weak base is going to cause the pH to rise. There's nothing new about that. But the difference is that if it's a strong acid or a strong base, remember it ionizes completely. If it's a weak acid or a weak base, it doesn't ionize completely, just a small percentage of it does that. So because of that, we're not going to be able to have a one-sided arrow. We're going to have that reversible arrow. In other words, we're going to set up an equilibrium situation. So just like we did with our equilibrium constants in doing our Rice tables, we're going to have to set one of those up for weak acid calculations. And another part of this is that we can calculate the percent of dissociation, how much of it actually breaks apart. And this is going to be our formula here. We look at our percentage, our concentration of our hydrogen ions divided by the concentration of the entire solution. This is at equilibrium. And then you multiply that times 100. Okay, first example. Sometimes some of the toughest parts of this is trying to figure out how to set up the equation, but it shouldn't be tough because you also know about Bronsted-Lowry acids and bases, and you know how to set up an equation for that. So in this first example, it gives us a concentration of a solution of a weak acid, and we're just calling it HA. That's obviously not a real formula for a compound, that's just a symbol for a weak acid, and we're told the pH of this weak acid. We want to find the hydrogen ion concentration for the solution as well as the Ka for the acid and the percent dissociation. So the first thing we need to do is set up an equation. If this were a strong acid, I would just say that HA, which is aqueous, is going to dissociate or break apart into its two ions, which would look like that. But it's not a strong acid, instead it's a weak acid, so instead of having a one-sided arrow, I have to have a double-sided arrow, so I'm going to set up a Rice table. It's possible for me to use this equation just the way I see it, or we can go ahead and set it up by adding it into water. So we've got our HA, we add it into water, it's a reversible reaction. And this is when you should start thinking about Bronsted-Lowry. What does an acid do? Remember, an acid is a proton donor. So this acid right here, HA, is going to donate its hydrogen ion to the water, to where that water turns into H3O with a +1 charge, and it becomes A-. Okay, so if I just make a little note about our phases here, everything is aqueous except for water, so water does not need to be part of my equilibrium expression. It does not need to be in my Rice table. These two equations that I have written down are really saying the same thing. I prefer to use the second one because when we get to bases, we're going to see that that is a little bit more helpful to write it like that. But overall, remember we said that these guys are telling us the same thing. It's telling us the hydrogen ion concentration. This is just a shorter way of saying the same thing, just like Bob and Robert. Same guy, just a different way of saying it. So now we can go ahead and set up this Rice table. Let's go ahead and label this. This is our reaction, initial concentration, change in concentration, equilibrium concentration. So we are told that we start off with a 0.21 molar solution of HA, and we're also told that there's a pH of 3.14. So if there's a pH of 3.14, then we can go ahead and do those calculations as well. So if we know our pH and we want to find our hydrogen ion concentration, we can say that our hydrogen ion concentration is going to be equal to 10 raised to the negative pH. So when we plug that in, we end up finding out that our hydrogen ion concentration is equal to 7.24 times 10 to the negative fourth molar. So that's going to be helpful because what we see there is that that's our hydrogen ion concentration, and that's going to be at equilibrium. So I can go ahead and plug that in also. And I would, oops, I can't write. There we go. 7.24 times 10 to the negative fourth molar is my hydrogen ion concentration. So that's what I'm starting with. Also means that I started with none of this and none of this. So I know that I can plug in some zeros for my initial concentrations on the right-hand side of my equation. So now I just need to figure out what my changes are. Just like we did with our equilibrium constants when setting up those Rice tables, we know that we've got to add to this side. You can't subtract from 0 here for a concentration, and subtract from this side. You can look and see that you've got to add 7.24 times 10 to the negative fourth to both of these, because again, you should be looking at those coefficients, but it's always, we're going to be working with just one of them for the most part. And then if we're adding that on the right hand side, we're going to be subtracting that from the left side. And I can fit this in right over here. Go ahead and plug it in your calculator and convince yourself of this, that when you say 0.21 minus 7.24 times 10 to the negative fourth, and you round that to 2 sig figs, it is pretty much equal to 0.21. So what we saw was that this value, this change, was really negligible. It didn't make a difference for us by subtracting that. It's still the same as our initial concentration. So now when we go ahead and plug all of this in, and we're going to solve for our case of A, we're going to say that it's equal to our product, 7.24 times 10 to the negative fourth squared, divided by our reactants, and that's just going to be the 0.21. And we do the math, and we get 2.5 times 10 to the negative 6, and that's our K value. The A here stands for acid, is what we notice. And then the last little bit of this, we're asked to figure out, to calculate our percent dissociation, and I think I can fit that right in here, that our percent dissociation is going to be equal to the concentration of your hydrogen ions, so here they are, divided by the concentration of your solution, here it is. So you just go ahead and plug that in, and you say 7.24 times 10 to the negative fourth divided by 0.21, and you take that and multiply that times 100, and we get a very small percentage that actually dissociates, that breaks apart, 0.34%. Okay, let's do number 2. Now, here's a blurry picture for you, but you have a copy of this that looks much better, and this is just to show you that you will have this handout, this reference sheet, to be able to refer to that shows dissociation constants for weak acids and weak bases. And if I just glance at example number 2, I see that I'm looking at acetic acid, which you can kind of see, it's right here, but you'll find that on your sheet, and it gives you some information about it. So here we can set it up again as a Rice table. We have to be able to set up an equation. We know that we're starting with acetic acid, HC2H3O2. We toss it into water, and in the process, those acids donate protons. We get hydronium ions, and we also get, in this case, acetate ions. Now, I'm not going to go ahead and write my phases on all of these, but you know that everything's aqueous except for your water, so we can cancel that out. And notice also how this is a little bit different than the first one that we did. We're, instead of just being given some sort of symbol of HA, meaning a weak acid, we're actually given the exact acid. We're told that it's acetic acid. So we can look this value up, its K value, on our dissociation reference sheet. And we see, in this case, that K sub A for acetic acid is 1.8 times 10 to the negative fifth. And so that's given to us. And we read through and it tells us that it has a percentage dissociation. We want to calculate the percentage dissociation, and we're told that we're starting with 0.44 molar. So this value we know. And that's pretty much it, except I know that I'm starting with none of that. So that's what we know. So it sounds to me like we're going to have to use some x's in this case. Obviously, you're going to have to add to this side and subtract from this side. You've got one of everything, which is what you would expect, because that's all we're doing is really changing these. Remember, conjugate acid-base pairs, they differ by one hydrogen ion, so it's really just going to be one of everything, how it differs. So we're adding an x to this side, and we're subtracting it from this side. So we went through that practice of seeing what it looked like when you did the math last time. When you said 0, well, here we've got 0.44 minus x, and on this side we have x's. So instead of making it really complicated math, what we can end up seeing is that this number is going to be negligible. It's going to be so small, it's not really going to change the value of that 0.44. So this is pretty much equal to 0.44. It does not change. And so we can go ahead and plug this in. We know our Ka, so we can plug this in and say that Ka equals 1.8 times 10 to the negative fifth, which equals our x squared over 0.44. And when you solve for this, you get x equals 0.0028. And that's your x value. The question is, what's the pH and what's the percentage dissociation? So by finding my x, what I have just found is the concentration of my hydronium ion, or hydrogen ion, and my acetate ion. So this is also, if I throw an M in there, that's going to be the concentration of my hydrogen ion. So I can take this information and I can solve for my pH because I know my pH calculations, my formulas. And I can say that pH is equal to the negative log of my hydrogen ion concentration. So it's equal to negative log of 0.0028. And when you go through that, you get the pH is equal to 2.6. You should be able to look at that and say, yeah, that's an acid. That's got a low pH. It's a value less than 7. We can go ahead and also calculate our percentage dissociation. And we see there that, remember for this, it's going to be the percent of your hydrogen ion, which is right here, which we know, right there. And it's going to be divided by the percentage of your, not the percentage, I'm sorry, the concentration of your solution. So that's going to be this value right there. So we throw those in, 0.0028 divided by 0.44, multiply times 100, and 0.64% dissociates or breaks apart. Last one. Notice that this is a little bit different. Now we see that this, we're talking about organic bases. Actually, the big word there is bases. And typically when we talk about weak bases, we're going to be talking about organic bases. The two types that you'll really need to worry about, the way that you'll see them, is that you'll either see a nitrogen that's attached to some sort of carbon group. That's pretty common. Or you'll see ammonia. So that's how you'll be able to identify weak bases. And again, remember that bases accept protons. So when we set up our reaction on this one, we're going to say that our Rice table, we set this up as, okay, it gives us, it says calculate the pH of, you know, this should say, have a big capital M there, 0.29 molar, and then it gives us this organic base there. So we should be able to write that organic base down. And again, think about what we always did. We threw it into water. That's the easiest way to do this. Then you think about your Bronsted-Lowry. What do bases do? This base is going to accept a hydrogen ion. And all you need to do as far as writing it, thinking about where you write it, just attach it on the end. So if you have an H, but that's not good enough. Remember, it's a hydrogen ion, so it has to accept that positive charge as well. So that's aqueous. And then the water ends up being the acid in this case, so that gives up a hydrogen ion. And, you know, really make this thing nice and pretty, it'd be nice to put aqueous with everything except for your water has the liquid. So we go through and we read about how we start with 0.29 molar base, and we have none of this. So that must mean we add, and we're just adding x. So we must subtract x from this side. But we know that this is negligible. It's a really tiny number, so it doesn't matter. It's pretty much going to be equal to 0.29, whereas these are going to be equal to x. So now we're going to calculate the pH, which means, the way I read that, is we've got to be able to eventually figure out either the hydrogen ion concentration or the hydroxide ion concentration to be able to get to pH. So I'm working with a base right now. I know that I can, I've got my sheet, my reference sheet that I can look at. I look up this compound and I see that my K value for that base is going to be 6.1 times 10 to the negative fifth. And then I set this up, I get x squared over 0.29. So my x ends up being 0.0042. And what that tells me is this. I'm sorry, I circled the wrong one. I was in the wrong place. So we've got an X there. What that ends up telling me is this. It tells me my hydroxide ion concentration. So if my hydroxide ion concentration equals 0.0042 molar, yeah, that happens to be this one also. But if that's my hydroxide ion concentration, then I can use that information to solve for. Probably the easiest way to do this is just to immediately go to pOH. So your pOH is going to be equal to the negative log of your hydroxide ion concentration, so the negative log of 0.0042, and that ends up being 2.4. So now you can easily say pH is equal to 14 minus 2.4, which gives us 11.6. And in fact, that's all it asks for. Doesn't even ask for a percent dissociation or anything. So we were really done at this point. But one of the big differences that I really want you to notice is that you cannot go directly from a hydroxide ion concentration to pH. Remember, that's going to take 2 steps, 2 different calculations, formulas for your pH calculations there. I think that is it.